it's going. Again, we're looking at page 43, and it should say something like center of mass strategy and a big table and all kinds of stuff. Okay, I'll get rid of this window. Okay, so I'm going to bring the book up really quick. Again, we're doing center mass. So this is a cool problem here, by the way, if you didn't see it. 9.24, it's pretty fun. All right, so this is basically a problem-solving strategy. I gave you it first, and it's pretty involved, as you can see. But one of the things that we need to do is basically we're going to try and do as little work as possible while still getting the job done. That's another name for this strategy. So first, if you know the answer without calculating anything, write it down. So, for example, at a rod, if you have a uniform rod, usually the center of mass is in the middle of an object. It's in the middle of a circular plate or in the middle of a sphere. Triangles, this technically should add an extra word. So in your book, you might add a word right here. This should say a right triangle. I guess I'm assuming we're talking about right triangles there. So it turns out the center of mass is 1/3 from the fat end. What do I mean by that? If you have a right triangle, again, it's got to be a right triangle. This is the fat end over here. So we actually see this end that I'm shading has a lot more stuff. So it'd be, let's see if I could split this into thirds approximately. It would be somewhere here. And interestingly enough, it's also, we could split it into thirds this way. We'd see it's right there. To me, that's a lot better than doing any of this stuff down here that's called calculus. So it's nice to use this technique. If you know the answer, write the answer. All right, that's a good thing to know. So, all right, let's get out of there. And then let's see what else. If an object is comprised of several known shapes, and this is really where step 2 comes in handy. Let's say you have an object that's made out of a rod, a square, and a circle. What we could do is we can use the point mass center of mass formula. This is a good time to mention that I have already made 2 YouTube videos myself, and I streamed these to they're on my YouTube channel, and I'll put a link to that somewhere in the chat in a minute. Or Trey, if you happen to know, it's Rob Jorstead AHC. If you could look that up and find my YouTube channel, I should have thought of that and sent that to you. It's Rob Jorstead AHC. You can find that somehow and put it in the chat. That would be awesome. Thanks, Trey. In this equation here, though, let's get back to this. If you have an object that's comprised of several known shapes, that would be awesome. You could do this. So M1 is the mass 1 of the first shape. This would be the center of mass of it. So let's say you had an object like, let me make one up really quick. Let's say you had a red triangle, and then you put on a rectangle on top. Or below it, sorry. You know the center mass of this one is here. That would be x2, and this would be, again, a third and a third, just trying to eyeball it. Probably about right there. You could use this. Oops, sorry, let's do this. This would be x2, and this could be x1. And then mass 2 would be this one, and this, et cetera, et cetera, et cetera. Mass 1 over here. Okay, so the idea is you'd use the trick from 2. If you know the common shapes, you could use that and this formula. So I'm going to leave that at that, and we could do examples later. Notice this is a cool trick. If you have an object with a hole cut out of it, this is usually where it comes in handy. For example, you may wonder in Physics 110 why I kept giving you these objects with holes cut out on test 1. What if you had an object that looked like this? Finally, we get to use that junk, and we also use it in Physics 163. So this is my attempt to shade. Apologies, I probably could have used a stamp, but I didn't. All right. In any event, so let's say we've got this object here. The idea is you could actually use M1, X1, where X1 is the center of mass in the X direction, for the triangle, and then you could actually subtract m2 x2 because it's a whole. So the idea is you could use this, you change this to a minus sign, and yes, that is also true in the basement. The idea is you could use the center of mass with actual mass or holes. Now, by this, it may not seem obvious. You should watch the videos that I made online after class if you want to, or again, this is next week, so we're trying to get ahead a little bit while we can. To be clear, and let me see if I just have my slideshow. I'm going to bring up my other slideshow, and apologies, I'm changing all over, but I think the picture I made in that makes a lot of sense. You know what? I don't remember where it is right now. I'm going to get lost. No, yeah, so crap. Sorry, I'm doing a bad job here. Let me just do it right here. To be clear here, this is what I want to make sure you understand. When I'm talking about mass one is the entire solid triangle, and mass two would be the mass of a solid circular hole. So this object right here can be split up into mass one and mass two. And you could think of mass two as being negative right here because it's a hole, not an actual object there. So we have to subtract out that little mass, and that's where these things come from. Yeah, more on that in a minute. None of this will make sense till we do a bunch of problems. Now, if you can't use these tricks up here, if you can't use any of these tricks, know the answer, or use these tricks with holes or whatever, we may have to use calculus. And so the videos, I made one video where you can use the point mass formula, and that's about 4 minutes long because it's pretty straightforward. And then I made another video where you have to do calculus. And then in your Canvas website, I put a nice picture showing and explaining the holes. So you can read about the holes in the Canvas website for week 12. We're talking about week 12 material now. That said, following this big, long procedure is complicated. You should watch the video, but maybe we'll get to a problem here in a minute and walk you through it. So I'm going to go ahead and go on here on, maybe I'll check the chat, see if there's anything in there. Okay. Yes, that's correct. Right on. Okay, thanks. Okay. And then, so let's keep scrolling down. Here's an example. This is actually a different example than the one I did in the video. So I made up a new version for the video. So this is a good one to do. And then you can watch the video and pause the video to the punch on every step of the calculation. So this is pretty straightforward. I don't want to blow your mind here. So let's just go right to it. I want to be clear here. X center mass has an implied I hat. You've been hearing that all day. It's a center mass position. Position is a vector. This has a J hat on it. So we could get plus or minus. Clearly, this has a negative value. What is each tick mark? It's 20. So it's negative 20 centimeters. It's not negative 1. We've got to read these tick marks. That means this is negative 20. This is negative 40, negative 60. All right. X2 is looking like 40. And I'm going to stop writing the units because it's hard enough already. 30, wait, I just screwed up. This is negative 60, right? I just screwed up. So, and let's just go to the solution so we're not killing ourselves here. Come on. All right. Somewhere we get to it. Oh my gosh, there's too much momentum going on here. Oh my gosh. Oh, there we go. That's a pretty cool problem, actually. That look how long that solution is. It's still going. I think that's a pretty challenging problem. It's still going. Jeez. So that was what, 925. I didn't put that on the list of required problems. All right. So here we go. Oh my goodness. Well, so those are the numbers that we plug in, and hopefully you could verify these numbers make sense. So it would help if you have your book to page 44 in front of you while you're looking at the solution. And so Yeah, have your book in front of you while you're looking at the solution. Notice there's a couple of minus signs right here and right here. And notice the kilograms are going to drop out because every term in the numerator has kilograms. It drops out. Ignoring sig figs, we get this. Uh, I don't know why I'm referencing Tom Petty, but that's cool. So hopefully your guess was pretty close. If we go back to there, notice it's -20 and -17. -20 and -17. It is worth going back and looking at where it would sit on the grid. So -20, I forget which was which, but it's somewhere pretty close to here. Hopefully it was -20 in the X and -17 in the Y. So I think that's what it was. If I was wrong, I'm sorry. But it's somewhere, well, I'll just go back and check. With the X, okay, yeah, X was -20. So it's right about here somewhere, right? 17 down, 20 over. And remember, 20 is one tick mark. So, and if you look at it now, yeah, it looks about right. Hey, here's a fun question, everyone. Center of mass. Shouldn't we have the same amount of mass on the left and right if it's the center of mass? Think to yourself if that should be true. Do you have the same amount of mass on the left and right of the center of mass? Short answer, no. Isn't that weird? So, yeah, you actually, in here, look, we know the X center of mass is exactly on this line. So the one is not left or right. And look at this. You have 3 kilograms over here and 2 over there. The center of mass is actually where torques balance in some future problems, as is indicated kind of here. Like you could see here, you don't have the same amount of mass here and here, but it is balanced and they cause equal torques. Torque is the next chapter. So this is foreshadowing a little bit. But yeah, center of mass, you do not have the same amount of mass on either side. Think about it. Do an even simpler case. What if you had 3 right here and 1 right here? I think you could agree the center mass would probably be pretty close to the 3, maybe about right there, a quarter of the way. Clearly, you don't have the same amount of mass. You have 1 on this side and 3 on this side. So do not think you should have the same amount of mass on the left and right. That's important to note. Okay, so if you want to, you could do this problem 9.28 at home, and that's great. I'm going to skip around a little bit, and I want to go to, I want to look at 9.32 for fun. That's at the middle of page 46. 9.2. It's this one right here. I'm going to scroll down just a little bit more. Oops. All right. So in this case, think to yourself, am I going to need to do calculus? That's what I want you to think about first off. You've got a circular plate with a hole cut out of it. Try to remember, do you need to do calculus or not? Hopefully you thought no calculus if I think of the hole as a negative mass and do a subtraction. So in this case, remember that this circle with the square, let me see if I can draw here. Whoa, Rob found a new toy. So we've got a circle and a square. Wow. It's almost like Microsoft Paint. You know what I'm going to do? I'm going to erase that and let's make it a different color. Let's go to format. How about blue? Draw that again. Sorry. So even though it's not perfectly scaled here, the idea is this. If you take the red circle and subtract off the blue square, you're going to get this right over here. So then this would be x1 equals, think to yourself, what is the value I should use for x1? X1 means the center of mass position of object 1. 0. It's right at the center. Now you're saying, wait a minute, how do I know it's 0? It's because you'll notice in a lot of these problems, there's a coordinate system included. So I'm usually going to include a coordinate system instead of having you choose. Why? Because in theory, everybody could choose a different one, and then the answer would be different on every single test. So we're going to usually see a coordinate system drawn on a center mass problem. And so over here, notice that X, whoops, sorry. We're going to go blue. So notice X2 is a little bit trickier. You got to do a little bit of geometry to figure it out. So at first it seems like there's really nothing to this problem, but now we see, wait a minute, the problem tells me this radius here is R, right? I need to figure out this spot. I know the hole is the center of mass of the hole is in the center of the hole. So what you have to do is relate this square to this only, this is the only given in the entire problem. The masses aren't given. This problem seems impossible. Hopefully you see this trick. That is the radius, isn't it? That is the radius because it goes from the center all the way out to the edge. Normally I have a piece of cardboard that I cut out and we can look at it and you can see it a lot better, but we don't have that. That's life. Okay. Well, so that helps you figure out this piece right here, and I'll let you do the work at home, but you could use some geometry to figure that out. The other thing that's confusing is, and I'm going to clear some of these annotations. Well, I won't yet. How do we figure out the mass? So let me talk about the mass. Mass 1, there's an awesome trick for these problems for plates with holes in it. We're going to use a new term for density. I'm going to call it sigma. This is lowercase sigma. It looks like a circle with a line going sideways. So sigma is this. Delta is this. Delta is the cherry bomb. All right. So sigma times area. Sigma is a new type of density. It's called area mass density. Sometimes people will call it areal mass density. But it's in units of, think to yourself, sigma. What are the units of sigma? This area mass density. Hopefully you thought, I'm starting to get tired. Hopefully you thought kilograms per meters squared. All right. So that's the sigma. And the idea is, this is what's crazy. This blue one here, you could think of it as having negative density. You could think of it as being antimatter, and this is matter. The red is matter, the blue is antimatter. Whatever, the fact is we could get M2 in a very similar way. Sorry, I'm writing all over this problem. I don't know what else to do here. M2 is sigma times area 2. And so that's a way you could get the mass. Now, I'm going to pop over to the equation and show you what this looks like because this is getting pretty painful for me. I'm going to go over to the solutions now. What problem was that? That was 9.32. Oh my gosh. Why didn't I just go to the solutions at the beginning? That was dumb. Okay, whatever. Well, that's what the solutions are for. Sorry about that. Anyways, so there you could see it a lot more clearly. And I wanted to point out, this is what's interesting here. Let me clear all these annotations. That was so painful. Sorry, I wasted all of your time. That was dumb. In this case, notice this term sigma appears in mass 1 and mass 2. And now we explained where you get these. Now I showed you the trick, kind of this radius right here. That's where you get this result right here. All right. And so when you plug these in, take a look right here. When you plug it in, hopefully you see that every single term has a sigma. And even though we don't know what sigma is, it cancels out. To be clear, if you're trying to figure out what sigma is, aluminum plates have a certain sigma. If they're 1 centimeter thick, sigma could be, I don't know, so many kilograms per meter squared. If they're even thicker, it's maybe more kilograms per meter squared. If you have a styrofoam plate, it'll have a different sigma. Sigma basically is talking about how thick the plate is and what material it's made out of. So sigma varies depending on what, so plexiglass, right? Depending on, yeah, okay. I think that's enough on that. Excuse me. In order to get things to work out, remember S was not allowed. We know the side of the square is, this is S over 2. Sorry, I'm having trouble here. S over 2. But the final answer has to be in terms of R because R was given. That's why this works out. And so hopefully, let's check. Does it looks like I maybe missed a minus sign here. Oh no, I'm worried. Let's check the units. I have R cubed on top, R cubed. And on the bottom, those both, I could factor out an R squared. Oh no, this looks like it's at least dimensionally correct. So we see this is something that could be useful in center of mass problems because you get so far into them. Unit checks are really useful to make sure the final answer, which is a position, should have units of meters, and it does. I'm going to let you guys try and do that one at home without too much more on it. There's some really cool stuff. This is something that it is kind of interesting to think about. Really quickly, think to yourself, where is the center of mass located? When you subtract mass over here, okay, obviously the center of mass is, whoops, sorry. The center mass of object 1 is right here. When you take this hole out, once you do this operation of subtracting this chunk, what's going to happen to the center of mass? Think to yourself where it will be. Hopefully you didn't see it on my slides. Is it up here? Is it up here? Is it down here? Or is it over there? So again, think to yourself, where is the center of mass located? The correct answer is actually right about here. It's very close to the center, but it is shifted slightly down and to the left. You have more mass down here and more mass over here. There's more mass over here and over here than there is over here. That causes things to be shifted that way. And I hope you agree, by symmetry, it should shift the same amount left and the same amount down. So I'll leave it for that. And I'm going to stop the screen share for a second and check in with you, see if there's any questions here. And you could give me, any comments you want if this is helping. Again, you've got extra videos, or if you don't need any comments, that's cool. I'll just check in and give you a chance. Have a drink of water for a sec.
So you were saying you have lecture videos on center of mass on your YouTube channel?
Yes, on that one that is listed here.
Okay.
Yeah, it should work. So, and it turns out those were the only videos that this other guy didn't have. So I think those might be the only videos I make, just because I'm spending nonstop time helping all the part-timers and everybody else, and like I'm trying to train people on Zoom, me. So yeah, it's been pretty crazy. If things calm down in a bit, I'll hopefully make some more if there's spot needs. But yeah, is that good, Ryan?
Okay, yeah, cool. Thank you.
Right on. Dane, I don't know exactly how much, but it's probably going to be something like I thought about maybe doing thirds. So like a third for the exam you turn in, a third for responding to the free response on the exam questions, and maybe another third for how you respond to, and some of it will just be for having some work done on those problems I told you to do, called the required problems. But yeah, I will dial that in. I'm not exactly sure what the ratio is. Maybe it'll be half and half. That might be a good way to do it too. So something like that. I just don't know yet. I will definitely let you know as soon as I do. I'm also almost ready to release the calendar for the scheduling, so maybe I should mention that to all of you. So in week 14, I'm not sure what happens when I update the Canvas website. Hopefully, you don't get an email every time I update it because I've been updating like crazy at all hours of the day and night. So, but hopefully, when week 14 gets posted, just keep an eye on it, and then uh, we will talk. You can then sign up for your exam appointment as soon as that is available, and yeah, you can look at week 14 for a link to that in a few days. Um, Mass is Sigma area. I don't know if it's on there or not. I don't think it is, Phil. Nope, it's not. So, and actually, that's a great thing to bring up right now, Phil. You should just, excuse me, you should just memorize it. I'm going to share my screen and show you what you want to kind of lock in for that. You're going to use it so much, it should be locked in, but whoops, that's the wrong one. Well, that's all right. It's this one. Whoops, this one. Look at this crazy chart. I basically am expecting you to internalize this. Why? I think center mass, it's kind of like kinematics. It just comes up a lot at weird random times. You've got to have this stuff internalized. So if you want, let's try and talk about this. If you have a 1D object, we give the density the name lambda. In some books, it's mu. Don't you love it? This mu is not coefficient of friction. It's linear mass density. It's very common. So we're going to try and use lambda in our problems, just so I don't have one more thing to confuse. So this is a Greek letter lambda. So 1D, you get mass per unit length. If you have a rod or a wire, or sometimes a rod could be bent into an arc, like one of the problems, I forget which one. And basically, when you're doing calculus, we're going to slice these things up, and we'll do one like that next. We'll talk about this. You're going to have these slices that come up with these terms like this. So for an arc, you get RD theta, and for you could have lambda dy. So check the units on this. You might be saying, what the heck is all this junk? This has units of kilograms per meter. I think you can see that pretty easily right there, mass per unit length. Over here, or right there, right? Now think about this. Mass in calculus, just because you're doing calculus in your math class without units doesn't mean that's right. You should be doing it the right way, right? Yeah, physicists. So if we do this, kilograms per meter times dx. Dx is a unit of length, meters. We see that this equation is dimensionally correct. So that's just a fancy way of dealing with the units. So the density has to have different units. Clearing that out. And then obviously here's the equivalent for 2D. Rho, your density. This is one that you've seen probably the most in a chemistry class or even in physics class. But so density, it turns out sometimes we will talk about area density or a linear mass density or a volume mass density. I'm going to check the chat real quick. Yep. Okay. He's got it. Thank you. Whoops. Okay. So now let's go back to, this is also a good spot if you have any questions, but so if you have them, keep them coming all the time. Let's take a look at this one. This is 9.30, the bottom of whatever page. All right. So in the video that I linked online, I did 9.23. So if you want to go through the solution, that's great, or you could watch the video. 9.23 is online. That shows you what to do if you had 3D calculus. So I just picked a random spot. Hopefully you remember, we already know the answer to that one. It's 1/3 from the fat end. However, the video walks you through the whole thing. Oh man. Sorry, I was up at 5 working. 9:30. Let's look at 9:30 now. Let's get back on task here. All right. So take a minute and think to yourself, part A, or talk to your neighbor or chat with your neighbor. So if you want to, we're going to do some calculus. And to remind you, the calculus formula, Here is the calculus formula that we're going to use. We're going to use x center of mass is equal to 1 over the total mass times the integral of x dm. All right, so I'll write that here so we have it. xcm is equal to 1 over the total mass. So I'll try and use capital M for that, times the integral of x times dm. In this case, or we could do, I guess you could say, well, I guess I just gave it away. We're going to end up doing y center of mass for this one. So it's going to be 1 over the total mass of y dm. And here's how I can tell right away. Look at this thing. In this equation, this is a tiny dimension. Oh, go ahead. What was that question, Ismail? Or if you needed something, let me know or add it in the chat. Sorry about that. I'm going to eventually get a tiny distance in the y direction, dy. So that's what makes me think, if I want to be able to do the integral and I plugged it into both of these, which one would I actually be able to compute? If you put in sigma dy, again, we're using sigma because this is a 2D. Geez, I keep giving away the answers. We're going to use sigma here because it's 2D. Sorry about that. So in this case, this is confusing to me. I don't know what to do. Clearly, this is not a good idea to do because I can't integrate x dy right away. You could actually do it, but you have to change what x is using an equation. Now here, if I plug in sigma dy, there's an integral that I can work this out. So this to me is an indicator I'm going to do a y center mass. This begs a question or brings up another point. I think this is important to note. Think about this. We're going to split this up into a purple chunk. We're going to add in a blue chunk here, and we're just going to keep splitting this thing into chunks. Think of this as exactly the same as that x1, m1 equation, right? The idea is we're adding up all these chunks. This would be mass 2, this would be mass 3 or mass 1, and maybe up here this is mass 3. Come on. And so the idea is we're adding up all these masses. An integral is simply an addition. It's another way of writing the sum. That's just a sigma notation, but we're doing a such small limit that we can do this trick called integral. In this case, when we add all these things up, I totally forgot where I'm going with this. Oh, we're doing a weighted average in the vertical direction. You could think of this as exam score 1, exam score 2, and exam score 3, and we're adding them up, and each one has a different amount of weight. Each one has a different amount of mass. So each one will affect the calculation differently. That's what this integral is. The integral of y dm says, tell me what the position of this is. Tell me your exam score, and then how much is it weighted? How much mass is actually at that height? So when you integrate that up and then divide by the total, you're taking a weighted average. The dividing by 1 over m is the averaging part. It's a weighted average. Hopefully that helps. Now, I'm going to get into the solution here because I keep screwing this up. But if you want, look at 9.c. This is one of the tricky parts. I know I'm throwing you into the fire here. Again, I've got 2 training videos on Canvas, and this is next week. I'm just trying to give you a leg up. So I'm going to clear my annotations here. Try to work out 9.30c. I'm getting tired. You probably are too. Let's see. Somewhere in here. There it is. Okay. So there's the comments that we just made. And here's what I was hoping you would come up with. I know I didn't give you enough time, so don't look at the screen if you don't want to know. The idea is this. We see there's a radius here. And I know that this x coordinate right here relates to this y coordinate using the Pythagorean theorem. Okay, that's cool. So this is true. Well, if I wanted to, I could figure out x, what that is, and that's fine. You might be saying, why would you do that? The reason is x is going to show up in the mass. Take a look right here. Oh, I didn't say this yet. So dm, I'm going to do this in a different order just so you can get a different feel for it than it's in the solutions. Remember that dm is sigma times dA. Here, I have a small amount of mass and I have a small amount of area. What does dA represent? dA represents this thing right here. It's the mass of this tiny area. D means differential or tiny amount. So that's dA. So sigma times dA has the units of, and I'll get to the question in just a sec. Remember, area, there's a length and a width there. That's going to give me kilograms, which is a small amount of mass. The terms we might use, we say dm is called the mass of our slice, dA would be the area of our slice, and sigma is the density of our slice. And I'm going to check the chat before I get too far ahead. Okay. Yep. Okay, super random. No. Yeah. Okay. All right. So there we go. There's that. All right. So I'm going to let me see, what was I doing? Oh, I was annotating. Sorry about that. Okay. So in this case, if I want to get dm, you see that I end up having to get dA. So I have to plug that in over here. And in order to get dA, I need x. So to get all of that, I'm going to take this, this equation for x and shove it in there. And now take a look at this junk. I see that I have an equation for A that's only in terms of y and constants. R is a constant, y is what we're going to integrate over. We're ready to actually do this integration. By the way, again, I want to mention that training video is going to clear up a lot of confusion because I'm skipping a little bit here, trying to give you some different problems, but the process is still the same. Oops. I'll check the, okay, so I'll check the chat in a minute. In any event, take a look. When you do this thing, we can plug in this crazy looking integral. Here it is, y center mass. That's the integral that I was trying to write earlier so sloppily. And here's what's tricky. In this problem, you probably don't know the mass of that plate. Look back at the word problem. Notice it doesn't tell you the mass. All it tells us is this radius. When you see a problem like that, where you do a center mass problem and they tell you a distance and there's no mass, that's a sign to use density. This is also a good sign. Maybe I should write the masses using density. The only way to do a mass using a density for this shape like this, where you have to do calculus, is like, where did it go? There it is. We write the integral of dm. Notice that mass and the integral of dm are the same. If I could use the annotation button. Actually, I'm going to scroll up first. So this 1 over mass becomes this. That's where that came from. And in this case, if it has uniform density, you just plug it in. You don't know what it is. Shocking. It's going to factor out right here and here, and then it's going to cancel out. At this point, you could do a trig sub, or you could use the integrals on the equation sheet. So I think there is actually one question on your test where I give you an integral table, by the way. So it's not an integral table. I'm going to check in with the chat now. All right. Okay. So, yep. Okay. All good. All right. Um, let's see. You know what? At this point, we're starting to get ahead, and I'm going to start going too fast if I plow ahead. I think this is a good time to call it a day, but I still have 15 more minutes. I'm going to stick around. If you keep going and this down, what I recommend, I will show you in Canvas what I'm talking about. So let me stop this. Let me go to Canvas really quick. Ah, all right, whatever. I'll do that later. Oh, geez. I tell you what, I'll take my screen off share and I'll get that done and then I'll share it back up again. You're welcome to take off anytime if you don't want to hear this boring end of the day stuff. And then let's see. Let's go back to the meeting and share my screen real quick. Sorry about that. All right. So in week 12, show you, I walked you through assuming you hadn't heard any of this lecture yet. So I wasn't planning on doing center of mass tonight and we just got ahead. So what I'll probably do is just let you watch these videos. And so we just watched this one. We did, yeah, you could check this one out. This is like the point particles. This one here, you could see the holes and how you might handle it. It's a different example, and it tells you which problems to try right after you watch these videos. Ideally, I would make a video that gives something to look at. This one is the calculus. It's a nice, long, slow one, and yeah, you could check that out. I recorded about 5 times until I got it right. All right, so there's that. At this point, we should probably stop doing center mass and we could either answer questions from the first part of chapter 9. We could do another momentum problem if we want to start it up, or you could just leave, or any questions you have about anything. So I'm going to open it up to you now. And if you want, you could turn on your video. There's not that many of us if you want to ask questions or leave it off. Oh. Hmm. And so it's looking like there's not a lot of questions. You can keep them coming. I like to try and make use of the time if we got it, even though I'm tired. I'm going to look at one more question and set it up or something, right? So I'm going to try and look at one more question, set it up. And oh, wait, there is a question. Oh, Phil, go ahead. If you have a question about the test, go ahead.
Oh, I'll just use my mic. So for the test, it's going to be a center of mass problem using calculus, like this one, and then just using the integral table to get the final answer is the way you're instructed that?
So if I did, great question. So the question was basically what type of center mass questions are going to be on the test, I believe. And so typically what I will do is there's going to be some problems that use calculus. And depending on which year it is, sometimes I make the center of mass problem use calculus, sometimes it doesn't. So you have to know both, and it's one of those. Phil, does that address your question on that part?
Yeah, that's good enough. Thank you.
I like to do questions like a lot of times I'll do a non-uniform distribution. I guess we should actually look at that. That'll be this. We should look at a non-uniform. So I love to do non-uniform distribution, which means the mass isn't distributed evenly. There's more mass on one side than another, say, and those require calculus. The other thing I like to do is, as you've seen, our problems with holes, just to see if people know that trick of using mass is equal to density times area. We've seen that twice already in 3 problems, I think. So let me share my screen and get into one that's non-uniform. If you want to get fired up on it, take a look at 9.33 through 33 and 2/3. Those are all on the required problems. I think everything I've done today has been on the required. I'm trying to stick to those. Apologies if I get a little bit off once in a while. I'm going to share my screen and get to it. see. I love 9.31. I'll leave you guys to do that one at home. We did this one. I hope you could see this is basically the discrete formula, right? You don't need to do calculus because you can do 3 shapes. I'll leave it at that. All right. Here's one with calculus. And I think if you do all 3 of these, this is pretty good. Yeah. I think there's another one on one of the next pages too. So one of the questions just says set it up and don't do the math. At some point, once you get good at these, you set it up and you're good. Look at how this works out. If you have something that has a non-uniform density, what does that mean? Look at this equation. If you have a non-uniform density on test day, you're going to get an equation for the density. The most common mistake people make with a non-uniform problem is they think lambda is mass over length. That is not true. Look at this. This right here, mass per unit length, is a constant. This is telling me right here, the density is not constant. Look at the picture. It gets darker. As I go to the right, more mass. Why? As X gets bigger, it gets more dense. That's all it is. So in a way, non-uniform density problems are easier than uniform. Why? Because the density is given to you in the problem. You don't have to figure it out. All right. In this case, we could do a center mass equation, and I'm going to jump over here to the solutions just to save myself some pain. Look at this equation right here. It's very straightforward, and you would do something very, let's get to the right problem. That would help. Oh, there's the calculus if you wanted it. We're on what, the next one? No, we did that one. Oh, shit. So this would be how the calculus looks. So I'll pop this up here and give you a second to digest some of it. The center. So if you've got the questions in front of you, just start working through this one. If you want to pair up with a neighbor and start grinding through it, this is a great time to ask questions about it while we're all here. All right. Based on the density function, we expect the center mass to be closer to the right end. Okay, so it should be bigger than L over 2. If I look at the unit math, don't forget those square brackets. Hopefully you see that the units of alpha make sense if they are kilograms per meter squared, right? Kilograms per meter squared times meter gives you back kilograms per meter. Remember, I'm looking at whoops, sorry, this right here, lambda is kilograms per meter. We're not talking about normal volume density, which is kilograms per meter cubed. If I want the total mass, don't overthink it. Shove in the density and integrate. dm, the mass of my slice, this thing in blue here is my slice. The mass of this particular slice is given by the density of that slice times the length of the slice. Again, remember, it's the kilograms per meter of that slice times the meters of that slice, right? What gets tricky here is each slice has a different mass. This one has almost none, and this one has a lot out here. So each slice has got a different mass, and that's why we can't just say it's in the middle. So because each slice has a different mass, this is just a fancy way of writing the mass of the slice. It's the density times its length. And when you do that integral, hopefully you get this number. I think you can do that on your own. To do the center mass integral, now we know this mass because we did the integral from right there. Again, we know that mass. Notice this always happens right here. There's an extra x in here compared to the bottom one. So if you do this right here, usually this is going to be something like, what is that? 1/2 alpha x squared, right? I love how whatever I say in these videos, 5 minutes later, I do the exact opposite, right? I'm not going to do any more center mass. I did center mass. I'm not going to do this for you. I just did it. Whatever. But here, notice you got to watch out. You got to remember this multiplication. That was the point. In this case, yeah, you're going to get an x squared. And so that gives rise to an L cubed over L squared. This drops out. This cancels two of those. And we get units of meters. And remember, this is a position, not a distance. Interesting. This actually looks a lot like a triangle. Notice it's 1/3 from the fat end, so to speak. Ooh, deep. A triangle changes linearly. That's the same thing as the density of a straight rod varying linearly. Ooh, deep. Okay. All right. I got to clear these annotations. This is getting messy. The fun part comes when you try to do 33 1/3 and 33 2/3. Those questions are, how would this change? Make sure you actually think about it before you look at the answers, because that's good training for the oral exam. What would be different if? And then think about it and do it. I'm going to stop sharing my screen. And then I'm about cashed out for the day. If you got any other questions, throw it in the chat. Otherwise, feel free to take off. I'll just stick around for a minute just in case. I don't know if we can give a big hand to Trey, but I'm going to try and do it here. I don't know if you guys see this. I'm giving a thumbs up to Trey. There you go, man. Do you see those, Trey, or no? All right. Yeah, there you go.
Yeah.
This actually helps me a lot when you can handle the chat. So that's cool. Do you have any parting thoughts any wisdom you like to think about? Anything you learned?
I felt like it was pretty good lecture.
Yeah.
Definitely do, which one was it? 928. That one was a very good practice question.
Yeah, totally. 928. Cool. All right, so I'm going to go ahead and end the meeting. Any more questions you have, go ahead and send them to me, and I'll probably take a few minutes to update those live streams. So go ahead if you haven't already done so, get to work on your labs, and we'll do all that tomorrow. All right, we'll see you.